Hi everyone, this is Marilyn Tournay and this is Teach Chem Forever. I just wanted to do this quick video to hopefully help you understand the assignment that you have to do a little bit better. So the first thing that we would have done if we would have gone into actual lab is we would have calibrated your glassware. That would have been experiment number 1. But since we're not there, what I want to do is I want to do an assignment revolved around the calibration of glassware. So you might be asking, well, why do we have to calibrate our glassware? And the answer is very simple. When you have a piece of glassware that you're using, the manufacturer will tell you that that glassware can hold a certain amount of volume. So you want to make sure that when you fill up, let's say you have a beaker, 10 milliliter beaker, and it says that it holds 10 milliliters of water, but when you fill it up to the 10 milliliter mark and you measure that, you weigh it, you see that you don't have exactly 10 milliliters and you've measured it correctly to the mark, but you have, instead of 10 mils, you have 10.1 mils. So that's okay. It's just that difference is really important. So you have to know that, so that every time that you use that beaker, you know now that when it hits the 10 milliliter mark, you know that it's not actually 10, it's 10.1. So that discrepancy will help you in the future whenever you're using that piece of glassware. And that sort of goes, that story is the same for every piece of glassware that you use in the laboratory. So I want to kind of go over a couple of terms, like I said, so hopefully it'll help you understand the assignment a little bit better. So I'm going to go ahead and put the computer down, but because I have to write, but I'm still here. All right. So let's pretend you have a pipette, right? And on this pipette, if you read it carefully, there's an indication, there's a writing on it, and it says that it holds 10 milliliters plus or minus, let's say 0.02 milliliters. Now, the 10 milliliters, this number here, is the indicated volume. Okay, and of course that's indicated by the manufacturer. So they're telling you it's supposed to hold 10 milliliters. Okay, great. This number here is the tolerance. Right? So the manufacturer is telling you, okay, you can hold 10, we guarantee that you hold 10 milliliters plus or minus 0.02 milliliters. Wonderful. So let's say you go to lab and you use this to measure 10 mils of water, and you get this. You get let's say 10.015 plus or minus 0.004 milliliters. So this is the actual volume that you got. Now, if you look at these two numbers, clearly they're not the same, right? So that's when calibration comes into play, right? So calibration, the calibration process, is basically helping to correspond the actual volume that you got to the indicated volume that the manufacturer says you're supposed to have. So it's sort of a process that compares those two volumes and gives you a true volume that you actually get with that piece of glassware. So the question becomes, what affects the actual volume? And if you think about it, temperature has a big effect on the motion of the molecules, right? So if you, for example, have water molecules at low temperature, right? These water molecules are going to have very small amounts of kinetic energy, right? So they're going to move sort of slowly at these low temperatures. But now let's say you have this same beaker, but you put it at a very high temperature. Well, these are my water molecules, and look what happens to the arrow, right? The arrow gets a little bit larger, indicating that now these water molecules are moving a lot quicker, moving quickly. In other words, the higher temperature does increase the velocity of those water molecules, which has a direct effect on the volume of the water. You guys have probably heard from when you study kinetic theory that, the higher the temperature, the more kinetic energy they have, the more velocity particles will have as well. So to drive this point home, let's look at some data that you can actually get from your book or the internet. But let's say we at certain temperature, degrees Celsius, if I want to know the volume of 1 gram of water in milliliters, right? The data that you can find is at 10 degrees Celsius, the volume of 1 gram of water will be 1.0014. At 20 degrees Celsius, it'll go up to 1.0029. At 30 degrees, it will go to 1.0054. So you can see clearly that as the temperature increases, the volume of the same amount of water increases. So in other words, the larger the temperature, right, the larger the volume. And that really should make sense to you. I do have a question that I want to ask you guys. So what effect do you think the temperature would have on the mass of or weight of water? And hopefully what you answered was none, right? There is no effect. So in other words, it doesn't matter if you have at 10 degrees or at 30 degrees, the mass of the actual water does not change. The mass does not change. The volume, though, you could see changes, but the mass or the weight of it will not change. And another thing to note here is that we should think about density, right? So density is mass over volume. But as we just saw, as the temperature increases, what happens to the volume? The volume also increases. If the volume increases, then what does that do? What does that do to the density? Hopefully, you can see by the equation that the density will decrease. Density will decrease. So as the temperature increases, you've got your volume of water that is increasing, but that in effect is making the density of the particular whatever you're looking at decrease. All right. So it's just a couple things to keep in note when you're taking these calculations in actual lab. So I wanted to do an example to try to maybe tie it all in together. So I'm gonna just go ahead and type up the example. All right, so I have written it here, and the example reads, an empty weighing bottle has a mass of 10.313 grams. After adding water from a 25 ml pipette, the mass weighs 35.225 grams. If the lab temperature was 28 degrees Celsius, what was the amount of water that you actually delivered by the pipette? So one of the things you should probably do is, before you start a problem, is ask yourself what's given. Well, clearly what they give you is the indicated volume, right, which is the 25 mils, and they give you these masses, the 10.313, and then after they added the water, right? So let's go ahead and write that down. So what's given is the indicated volume and the masses. And your goal here is to basically from these masses, find the actual volume that was delivered. That's what your goal is, right? The goal is to take these masses and convert it to the actual volume that was delivered from this pipette. To do that, you're going to need a table, right? The table that converts temperatures or masses into volumes. So you can find that in your book from your lecture, or this table would be given to you, obviously. So let's take the mass of water that we have, which is simply using the 35.225 grams minus the original weight of the weighing bottle, which was 10.313 grams. If you do that math, it should give you 24.912 grams. Now, to convert this to actual volume, you need that table I was talking about. Which converts masses at certain temperatures, masses of water at certain temperatures, to volume of water. So by looking at that table, you'll see that at 28 degrees Celsius, the conversion factor would be 1.0046 milliliters per gram. So this is what we would use with our mass of water to help us figure out how much volume we actually delivered. Now, let's go ahead and do this in red. So you would take this 24.912 grams and then multiply that times the conversion factor, which is 1.0046 milliliters per gram. That should give you 25.027 milliliters, right? Because the grams cancel. Milliliters of water that's actually delivered at 28 degrees Celsius. So it's look at the indicated volume and look at the actual volume that was actually delivered in this 25 ml pipette at 28 degrees Celsius. So you might be wondering how close is this actual value, to the indicated value, and that is very simple to figure out. So what that's asking you is, how accurate is that pipette, right? So what is the accuracy of your pipette? So the way that we would calculate that would be percent accuracy is equal to the experimental value minus the true value over the true value times 100. The true value is your indicated value, right? So the thing that the manufacturer tells you. And the experimental value, in this case for us, is the actual value that we got. So once you know that, then this becomes really easy, right? Because all you do is actually plug in all the numbers. So the actual value we got was 25.027 milliliters minus the indicated that the manufacturer told us we should get. It's 25 milliliters, one sig fig, and divided by the true value, which is 25 milliliters times 100. When you do that calculation, it gives you 0.108%. And if you notice, this is way smaller than 3.5%, which is a typical value that you want to be under. So it's quite, you could say that this pipette is actually quite accurate. It's really good. It's really good at its accuracy at delivering volumes, right? So if it's less than 3.5%, then you're good. And this is way, way below 3.5%. So it's a pretty good, accurate pipette. And your pipetting technique is actually pretty good as well. Hopefully this helps you understand a little bit more why it's so important for you guys to actually calibrate your glassware. See, these little temperatures and the temperature of the water, the temperature of the room, all of this stuff can actually make a big difference when you're doing calculations, especially in quantitative analysis. But for the most part, this is the one of the most important things that I think would help you for this assignment number 1 that we're doing. So that is all for today, and hopefully you guys thought that was really helpful, and I will see you next time. Thanks for listening.